Hi, Ofer. Can you hear us?
Hi.
Okay. Good. I guess we need to use the mic. Ofer, you'll be using these two boards, moving them up and down, or okay.
We are very happy to have Ofer Aharony today for the ICTS string seminar. He's going to talk about type 2 string theory on AdS3 S3 T4 and its CFT dual. Please take it away, Ofer.
Okay. Good afternoon. Thanks for the invitation to give this talk. So today I'll review type 2 string theory on AdS3 S3 T4, and this will mostly be based on this paper that I did a few months ago in collaboration with my former student, Ulbach. And this will be a Blackboard talk, so I'll try to go as slowly as I can, and please do interrupt me often with questions to me, especially in a Zoom talk. It's very important so that I can tell that if you're following or not. So this example of holography is in many, well, it's one of the original examples of holographies from Maldaceno's original paper, and in many ways it's the best understood example that we know of holography. It shares with n equals 4 super-Yang-Mills the property that there's one limit of the parameters where the background is weakly coupled and weakly curved, so that we can just approximate it by supergravity. And then there's another limit of the parameters where the field theory is weakly coupled and free. In this case, it's just a free symmetric orbifold, as I'll review. So it has these very nice properties in common with n equals 4 super-Yang-Mills, but it has the extra advantage that the string worldsheet is understood much better, again, as I'll review, and therefore we can say much more about string perturbation theory in this case. And the reason that we went back to studying this very well-known example is that we were confused about some aspects about how string perturbation theory acts in this background, and hopefully we managed to understand them, so that's what I'll describe. But I'll start my talk with a review that will take probably more than half of the talk of some of the many things that are known about this example. So I'll review these theories from 3 different perspectives. First from the perspective of supergravity, then from the perspective of the dual field theory, and then from the perspective of the string worldsheet. I'll then review what's known about the dualities that relate to different AdS3 S3 T4 backgrounds of this type. And then in the remainder of the talk, I'll focus on 3 questions that we were confused about, and that hopefully will become clear also during the review. So one question will be what happens for the special case of Q5 equals 1 when the string coupling becomes strong? How is that realized on the CFT side of the duality? A second question will be what exactly does the SNS string perturbation theory compute? And the third question will be whether the CFT includes, in this case, a decoupled sector, and how is this possible because it contradicts the usual lore of AdS CFT. So let me begin with a general setup. So like in other examples of AdS CFT, we can construct this theory by taking the near horizon limit of some rate configuration. So we can start type 2b on T4. We could equally well be in type 2a because they're related by T-duality. So for simplicity, I'll just discuss the 2b case here. And we can start with having a Q5 D5 branes that wrap the T4 and Q1 D1 branes that are parallel to them. So this is a specific brane configuration that preserves 1/4 of the supersymmetry of type 2b string theory or supergravity. So all in all, it preserves 8 supercharges, and in this case, that means that it preserves n equals 4 supersymmetry from the point of view of the 1 + 1 dimensional theory on the dimensions that are shared by the D1 branes and the D5 branes. So this is some BPS brane configuration that we can start with in type 2 string theory, and then when we take the near horizon limit of this brane configuration, then we get type 2b string theory on AdS3 and S3 T4. I mean, so the T4 essentially goes for the ride, and the 6-dimensional space becomes AdS3 S3, where we have Q5 units of D5 brane charge on S3, and similarly we have D1 brane charge, which is given by the integral of star F3 on S3 T4. So we have Q1 units of D1 brane charge and Q5 units of D5 brane charge. Now the fact that we have in this case 2 different types of fluxes, unlike the simplest examples of say AdS5 S5, means that when we solve the gravity equations, we can see that some of the scalar fields become fixed when we take the near horizon limit, even though in the original type 2 string theory on T4 they could take any value. And in particular, if we compute the parameters that we find for this AdS3 S3 T4 background, we find that the string coupling, which I'll denote by G10 to denote the 10-dimensional string coupling, can take any value in this near horizon limit. The radius of the AdS space, which is the same also also as the radius of the sphere is fixed to be the string coupling times Q5 in units of the string scale. I'll denote the coupling and string scale in this frame by tildes, because I'll soon discuss a different duality frame where I won't use tildes. And it turns out that in this AdS3 background, the volume of the T4 is fixed when we take the horizon limit to be just the ratio of Q1 over Q5 in string units. Of course, we could always, if we want to do a T-duality on this T4, but that T-duality it exchanges the two types of d-brane charges, Q1 and Q5, and so that's consistent with this relation between Q1 and Q5 and the volume. And we can also, since well, 4 of the dimensions are compact, we can look at the value of the 6-dimensional string coupling. So as usual, we can define a 6-dimensional coupling by the volume of the T4 in string units times 10-dimensional string coupling, and then some of the equations become simpler in terms of the 6-dimensional string coupling. For instance, the radius squared of the AdS is the 6-dimensional string coupling times Q1, Q5 in string units, and we can also write it in the 6-dimensional Planck units as Q1, Q5 times the 6-dimensional Planck scale squared. So I'll denote n to be Q1, Q5, and then this relation between the AdS radiuses and the Planck scale is actually exactly the same as what we have also in AdS5 process 5. It just tells us that to get a large radius in Planck units, then this n, which is Q1, Q5, has to be large. So this is what we find just by solving, if you want, the supergravity equations for type 2b supergravity on AdS3 process 3 cross T4. And,
just to check, so the reason you're putting tildes on this is because there'll be some other frame you'll introduce.
Exactly, yeah. So that will be on the other side of the
And
blackboard.
among the
That's
symbols
right.
you've written now, only G10 tilde is a modulus, right? Everything else is determined.
Yes, exactly. So Q1 and Q5 are just fixed integers, and indeed, exactly, only G10 is a modulus, but of course there are also other moduli that I'm suppressing, like the shape of the T4 and so on, and I'll describe the full set of moduli a bit later. But yeah, from the parameters that I wrote down now, only G10 is a moduli, exactly.
Okay, thanks.
So we see here that supergravity is valid, so of course for supergravity to be valid, then we need that Q1, Q5 has to be much bigger than 1, and also the radius, and also G tilde. Times Q5 has to be much larger than 1 for this AdS radius to be large in string units. And then if we want also string perturbation theory to be valid, then of course G6 tilde and G10 have to be small. At least naively, again, we'll see it later that there are some caveats to this. So this is one description of this background. Now we can perform an S-duality of type 2b string theory and describe the same background with an S fluxes, I mean H3 and star H3. Or alternatively, we could just start from Q5 and S5 range in type 2 string theory and Q1 fundamental strings and take the new horizon limit. I mean, that's of course related by S-duality to the previous case. So in this other, so again, this is just an equivalent frame to look at the same background, I mean, related by S-duality. And of course, the 10-dimensional string coupling in this frame is just 1 over the 10-dimensional coupling that we had in the other frame. And then if we translate the parameters, then we can see that in this frame, the AdS radius is just given by Q5 times the string length squared, with no extra factors of the coupling. And it turns out that, so in this Ramon 1 frame, the string coupling constant was free while the volume of the T4 was fixed in the new horizon limit. But it turns out that if we do this S-duality transformation, that it turns out that the 6-dimensional string coupling is fixed in this, what I'll call an SNS frame, because it has an SNS fluxes. So in this frame, the 6-dimensional string coupling is fixed to be exactly Q5 equals Q1, while the volume of the T4 is arbitrary. So that's, again, it just follows by S-duality from the other frame. And of course, well, one can check that it's consistent with the usual relation between G10 and G6. And this description, so this description is weakly coupled if Q1 is larger than Q5. Then this description is weakly coupled. And of course, supergravity is valid if also, so if this is also much bigger than 1, then the supergravity approximation is valid and the curvatures are small. So that's sort of the first brief overview of the most important parameters in this background. So are there any questions about this so far?
Yeah. Anything? So the relation between G10 and G6 now doesn't just involve VT4.
So it's the same relation, right? So 1 over G6 squared is VT4 divided by the string frame times G10 squared. The usual relation of the 6-dimensional and the 10-dimensional string coupling. And you can sort of see that, I mean, in one of the frames, G6 is fixed while the volume varies, and in the other duality frame, the volume is fixed, but G6 varies. I mean, so it's.
So you mean the volume of T4 and G10 have to vary in a coordinated way?
Exactly, such that the relation between the 10-dimensional string couplings is in this way. And you can actually, well, it's obvious from here that, I mean, what looks like this 6-dimensional string coupling is in this frame is, or the inverse of the 6-dimensional string coupling in this frame is mapped to the volume of the T4 in this other frame. So going to recoupling in this frame also means a lot of volume in that frame, and vice versa. Again, those parameters are just fixed by the fluxes at Q1 and Q5.
Okay, thanks.
So any other questions about this supergravity perspective? Okay, so if not, then let me now describe what we know about the superconformal field theory that's dual to this AdS3 background. And so as usual, when we have a new horizon limit, then the conformal field theory is just given by the Lorentz theory limit on these branes, and I'll use the D1, D5 system here for simplicity. And then if we look at low energies on the D5 range, then we have just a UQ5 gauge theory in 5+1 dimensions, but wrapped on this T4. And from the perspective, so the D5 range give rise to a UQ5 gauge theory. And from the perspective of that gauge theory, the D1 branes look like Q1 instantons of this UQ5 gauge theory. And one can show that at low energies, the only massless fields are just the coordinates of the moduli space of these instantons. So we have D1, D5 strings that we can turn on, and that make these, I mean, if we just put in D1 branes, then they would be like zero-size instantons, but when we turn on expectation values for the D1, D5 strings, then the instantons become large. And one can show that the precise low energy theory is an n equals 4 for supersymmetric sigma model on the moduli space of instantons. So on the moduli space of Q1 instantons. Of UQ5 on a torus. And there's enough supersymmetry here so that the metric on this moduli space actually doesn't get any quantum corrections, and one can show that it is indeed, the sigma model is indeed a superconformal field theory. So that's at least one way to describe the superconformal field theory, which is dual to these backgrounds that we discussed before. Now let's ask what's the dimension of this moduli space. So the dimension of this moduli space, it has one contribution from the space of Q1 instantons inside SUQ5. I mean, so we could look at instantons in SUQ5, not involving the U1 part, and it's well known that the moduli space of Q1 instantons of SUQ5 on a torus has dimension 4 times Q1 times Q5. And then there are 4 extra moduli in this case that come from just Wilson lines of the U1 factor in UQ5 on the torus. I mean, so those Wilson lines just commute with the SUQ5, so they essentially don't talk to the instantons. So we have 4 additional moduli just coming from these U1 Wilson lines. So the total dimension of the moduli space is 4Q1, Q5 plus 4. And then that means that the central charge of the sigma model, again, there's enough supersymmetry here to ensure that nothing is renormalized. So the central charge of this superconformal field theory is 6Q1, Q5 plus 6. And of course, in the limit of large Q1 and Q5, that's consistent with what we would get from this supergravity description before, where the radius was given by square root Q1, Q5 in Planck units, and that is consistent precisely with this central charge.
Ofer, can you hear? I have a naive question. You mentioned something about point-like limit of these instantons. Could you say more? Just
about what? Sorry, yeah.
Basic question. Hello?
Yeah. Can you please repeat the question?
The question, you said something about the zero size limit of the instantons, and that corresponded to something.
Yes.
Could you repeat?
Yeah. So we'll discuss more of the zero size limit first. I was just saying that if you just have these D5 branes and you just put a single D1 inside them, then just putting in a D1 inside them, the way that it couples to the D5 brane field is just like a zero size instanton. But then there are strings stretched between the D1 branes and the D5 branes, and one can show that giving an expectation value to these strings has the property of blowing up this instanton to be a finite size instanton. So in particular, generic configurations, and these D1, D5 strings are all massless and so on, so generic configurations of the massless fields correspond to generic points in this moduli space of instantons. But it's true that there are specific singularities when instantons go down to zero size, which I'll discuss more extensively later.
Thanks.
So indeed, one problem with this CFT is that in general it is a very complicated CFT. I mean, the moduli space of instantons is a very complicated space, and indeed it has some singularities when some of the instantons go to zero size, and so it's a rather complicated space. But one interesting thing is that there is a special case where this moduli space simplifies, which is the case where we have just one 5 brane, so Q5 equals to 1 in my notations. So if we have just one 5 brane, then we have instantons just in a U1 gauge theory on a torus. If we have a U1 theory, then there are no finite size instantons. All the instantons are always zero size. So in this case, the moduli space becomes just so the instantons are all of zero size and they can live anywhere on the torus. So we have T4 to the power of Q1. But since they're identical, then the moduli space of the instantons becomes, in this case, just T4 to the Q1 mod SQ1. And on top of that, we have an extra 4 moduli from the Wilson lines, and they live on what's actually a T-dual torus, if you just follow the periodicities. So in this case, the full CFT is just a sigma model on this symmetric orbifold times an extra torus. So in this special case, the CFT simplifies, and it has this very simple description. Well, for general Q5, it is a very complicated space that has some singularities. Now, just from this description of the metric, it's not obvious what happens at the singular points of this, at the fixed points of this symmetric orbifold. They may either be singular or not, but I'll review later the evidence that in this case, actually, there's no, the theta angle at these singular points is equal to pi, so that it's a non-singular orbifold, and the claim is that we really have this free orbifold arising in the CFT in this special case of Q5 equals to 1. So that's a special case where, and again, in this case, it's essentially a free field theory, of course, because we just have a free orbifold of just 4 periodic scalars and free fermions. So in this case, the CFT is just a free theory. So that's a brief description of the CFT side. Now let me say a few more words about what are the symmetries of the CFT. So of course we have then equals for superconformal symmetry, and then equals for superconformal symmetry contains an SU2R symmetry, both for the left movers and for the right movers, and that maps on the gravity side to just rotations of the S3 that we see in on the gravity side. But there are actually several other interesting symmetries. So because we have because we have some compact scalars in this sigma model, then they give rise to U1 affine Lie algebras. So from the center of mass position of the instantons, so the center of mass position of the instantons is just a periodic scalar. The center of mass can be anywhere on the T4, and it turns out that so the center of mass of the instantons gives rise to 4 periodic scalars, which give rise to U1 to the 4th plus U1 to the 4th left moving and right moving U1 symmetries, which are of level Q1. I mean, you can tell that because you have Q1 instantons, then the U1 symmetries turn out to be of level Q1. And then there are extra scalars coming from the Wilson lines, and the Wilson lines, they're also just periodic scalars, and they give rise to U1 Q5 to the 4th plus U1 Q5 to the 4th. Kac-Moody algebras, so the full Kac-Moody algebras that we have, I mean, on the left and on the right, we have an SU2, and we have 8 additional U1 symmetries, 4 of level Q1, and 4 of them are level Q5, so the occurrence of these symmetries by J, and the occurrence of these symmetries by J tildes, all J and J bar, and J tilde and J tilde bar. Now, I guess in the special case of Q5 equals 1, of course, it's completely obvious that, I mean, we have just a sigma model on a torus that gives rise to U1s of level 1, and we have the symmetric orbifold where the center of mass gives rise to these Kac-Moody algebras at level Q1. Now we can ask where do these symmetries show up on the gravity side, and we can easily see them also coming out from type 2 supergravity. So if we look in the SNS description, so in the NS description we have so we're supposed to see on the gravity side also that we have 16 U1 gauge fields. So in the SNS description we have 8 gauge fields which come from the GBI components of the metric and of the B field. So each one I here goes over the 4 coordinates of the torus, and U can go over, say, the AdS3 coordinates. I mean, so those components of the metric and the torus give us 8 U1 gauge fields, and one can show that these fields have level Q1, so that they match with these fields. And in addition, we have 8 Ramon-Ramon U1 fields that come from either the Ramon-Ramon 2 form or from the Ramon-Ramon 4 form. So those would be the fields that usually these strings and these 3 bands are charged under. And those so that gives all in all also 8 extra U1 gauge fields, and those 8 extra U1 gauge fields are related to these U1 Kac-Moody algebras that we have in the CFT at level Q5. So it can show, so already in supergravity, one can show that these U1 gauge fields, so they have Chern-Simons terms, which just come from writing down the supergravity action on this AdS3 cross S3 cross T4 action, and those Chern-Simons terms have the appropriate level such that these U1 gauge fields are dual to U1 Kac-Moody algebras at level Q1 and those at level Q5. So that's something that one can just see in gravity, and of course, again, as usual, of course, the symmetries match between the 2 sides. So that's some basic facts about the CFT side of the duality. Are there any questions about this?
Maybe another naive question. So is it easy to see that for example, the level of the first U1 to the 4 is Q1? I mean, so the U1 current, I'm guessing, is just some partial X, right? Like.
So it's easy. I mean, in this description of the free orbifold, it's easy. I mean, you're asking for more general values of Q5.
Or I guess even there, what does the level really encode for a U1? Does it?
So to see the level, well, you basically have to see what's the. I mean, so here we have the center of mass field. So essentially, here this one can be described in terms of the scalar fields that are the center of mass coordinates of this orbifold. So in some sense, they're the sum of the Q1 coordinates on each of these tori, and then essentially this level. I mean, for a fixed periodicity, then the level is just related to what's the coefficient of the kinetic term, and then because we have here a sum of Q1 different scalars, then it just gets level Q1. So whenever you have a free orbifold of this type, and you have, say, a U1 acting on inside each copy of the T4 separately, which is of level 1, then when you take the sum of all of them, you just get that it's of level Q, that the Kac-Moody algebra is of level Q1.
It's encoding the radius of some compact scalar field, this Q1.
Yeah, so of course you can also think of it as the radius. That's right. I mean, yeah. So right. So each one of those also has some periodicity, of course, which would correspond to its radius, and then so I mean, if you fixed it at a fixed value of the radius, then this Q1 would be related to the radius. I mean, but in general, each of these scalars can have any radius. I mean, it can be a symmetry in T4. So the radius is sort of related to the periodicity of the scalar field, and this Q1 is more like the coefficient of the kinetic term. I mean, and when you have some fixed periodicity.
And about the Q5 level, is that?
Another way to describe it is that it sort of tells us, I mean, of course, it's related to which values of the momenta and winding are allowed. I mean, and so you can just match the spectrum of the sort of diagonal T4 in the free orbifold with the Kac-Moody algebra, and you can show that the spectrum of momenta and windings that you find are exactly consistent with this level for the Kac-Moody algebra. So yeah, I don't have a very simple way to see that, but it's just a property of symmetric orbifolds. If you take the sum, then it's easy to see that it obeys. I mean, that when the currents are quantized so that the charges are equal to 1, I mean, then yeah, you can show that the 2-point function of the currents is proportional to Q1 in this case. I mean, again, I guess that's sort of obvious because it's just the sum of Q1 independent tori, for each of which, when the charge quantized to 1 has level 1, and then the sum of all Q1 of them would have level Q1. And similarly for the Wilson line, it's lives in a UQ5, so in some sense it's also the sum of Q5 independent U1s, and then you get this level. So I hope that answers the question. Okay, any other questions about the symmetries and the CFT? Okay, so the final perspective that I want to describe is the string worldsheet. So again, the nice thing about this background is that we also understand the string worldsheet nicely. Of course, in the Ramon-Ramon case, we don't understand it very nicely, like in other backgrounds. In the Ramon-Ramon case, we can describe it in the hybrid formalism or Green-Schwarz formalism or other formalisms, but it's not very well understood. But if we look at the case with an SNS fluxes, then for that case, we do have a simple worldsheet description. One way to describe the worldsheet is just in the usual RNS formalism of superstring theory. And in that case, the matter fields on the worldsheet are just given by a product of an SL2 WZW model at level Q5, which describes the AdS3 factor with the Q5 units of flux, of free-form flux. It has an SU2 WZW model at level Q5, which corresponds to the S3, and it has just a single model on the T4. So the CFT in this case is very simple, and it's described in terms of solvable conformal field theories. So in principle, we know everything about it. So that's the worldsheet CFT in this case. And again, we just put a type 2 superstring, so we have the supersymmetric version of this worldsheet conformal field theory. Now it turns out that the supersymmetric SU2 WZW model at level Q5 is the same as the bosonic SU2 WZW model at level Q5 minus 2 plus 3 fermions. So this description in terms of the supersymmetric WZW model really only makes sense if Q5 is bigger or equal to 2, because otherwise we get it becomes singular. But whenever Q5 is bigger or equal to 2, then this description is good. And then if the string coupling is small, we just have more or less a standard string perturbation theory, just with a specific worldsheet conformal theory living on it. Now, even though it is in some ways a standard string theory, there are other aspects of it which are not so standard, and which I'll focus on in most of this talk. And one aspect of this string theory that is not so standard is that one can show that it has a continuous spectrum of states. So even though usually we think of AdS3 as a compact space, say if we talk about AdS3 in global coordinates, and we would think that the spectrum should be discrete, then in this case, if we compute the string spectrum, we find that it's actually continuous, and that's related to specific configurations that are called long strings. So if we have a string that winds around the circle, so here I'm drawing AdS3, and this is the boundary of AdS3, which is an S1, a spatial S1 cross time. So if we have a string in the bulk that winds around this S1 close to the boundary, then naively, when the string becomes large, it costs a lot of energy because of the string tension. But in this specific background, this is almost exactly cancelled by the contribution from the B field, which decreases the energy of the string, so that these strings actually have a finite energy, even when they go all the way to the boundary, so that their momentum in the radial direction gives rise to a continuous spectrum. So that's one strange feature of this CFT. So we can see it in space-time from these long strings. I mean, in the CFT itself, it comes just from the fact that the SL2 WZW model itself has a continuous spectrum, and then when you look at the physical states, you find that they also have a continuous spectrum in this case. So from the space-time point of view, this continuum comes from these long strings. On the worldsheet, it comes from the continuum of this SL2 WZW model. And if we go back to the CFT that we discussed before, so the CFT, a priori, we wouldn't expect a continuum because this is just a single model on some compact space. So in this case, the continuum arises because this space actually is singular, as we mentioned before. So this moduli space has small instanton singularities for Q5 bigger or equal to 2 when we have an non-abelian theory. Then we can have finite instantons, but we can also have instantons that become small. So there are small instanton singularities, and these singularities look like orbifold singularities that, even though in the classical metric they just look like orbifold points, but in fact there's a vanishing B field at that orbifold, So one can show that there are actually singular CFTs that have a continuous spectrum. One can write down some change of variables where it will look like the space-time develops a semi-infinite throat close to those singular points. So that also from this perspective, we can see that we have a continuous spectrum of modes going close to these singularities. So we have, again, three different perspectives on this continuous spectrum, either as long strings in space-time, or as fields living close to those singularities in the CFT, or just as continuous modes of the SL2WZW model from the point of view of the worldsheet theory. So that's one strange feature of string theory in this background, and we'll see another strange feature a bit later. So this is one way to describe a string background, which is only valid for Q5 bigger or equal to 2. Yes, any questions about this?
Yeah, so the question is, but this is kind of infinite distance in moduli space, right? So you'd like to somehow move away from this point and not see this continuum. So, should we really...
on the moduli space, it's not infinite distance, it's finite distance. At finite distance on the moduli space, you develop this throat. So for instance, in some simple cases, the singularity is just an R4 Z2 singularity. Say if you have a single SU2 instanton becoming small, and then the singularity just corresponds to taking the the Fed angle or the B field on the vanishing 2 cycle here. So when you take the B field on the vanishing 2 cycle to 0, then the CFT becomes singular. But this is a finite distance in terms of the conformal moduli space. It's not an infinite distance.
Okay.
So it's a finite distance, and at finite distance you open up this semi-infinite throat that becomes that leads to a continuous spectrum. But it's not infinite distance in the conformal moduli space of parameters of the CFT. That's important.
I see. Okay, thank you. But even then, shouldn't we try to move away from this singular point in the moduli space to try and understand the theory?
Yeah, so I'll discuss in a moment exactly what happens when we move away from that point. So for now I was focusing on just the subspace, I was implicitly focusing just on the subspace of the full moduli space of these theories, and I'll discuss the full subspace in a few minutes.
Thank you.
So I hope that will become clear in a few minutes, but yeah, for now we're just sitting at this specific subspace where we only turn on, where we didn't turn on any other scalar fields except for the dilaton and the moduli of this torus. And on that subspace, the CFT is singular and it has this property, but yeah, I guess it's already obvious from here that it should be possible to turn on moduli that resolve the singularity and that then lead to a theory that doesn't have a continuum, and we'll discuss in a moment how to do that.
Hello? Which space has this throat? Sorry, I get this R4 mod Z2 singularity is in this moduli space of instantons?
That's right.
But where is this throat?
So the throat is just another way to describe. So if you describe it in the original variables, say the variables coming from the D1, D5 strings, then you can show that you just have a singularity and it's a singularity at a 0 theta angle, and so it's a singular CFT, and we don't really know how to analyze it. But it turns out that close to the singularity, you can change variables to another set of variables, where you do see that you have this throat. So I won't have time to discuss this in any detail, but one way to see that is that if we're talking about instantons on R4 and not on T4, then you also have similar small instanton singularities, and in those cases, the sigma model on the moduli space arises from the Higgs branch of some Q1 theory with Q5 hypermultiplets. And in that case, you can show that the Higgs branch has these singularities, but at these singularities, it connects to a different Coulomb branch in the moduli space, and then you can use the Coulomb branch variables to see that there is indeed a semi-infinite throat at these singularities. So that's a bit of a long story that I won't have time to go into today, but I can give you references to it if you want. So there is an explicit change of coordinates you can do close to the singularity to a different set of coordinates, where you can show that indeed there is a semi-infinite throat. And yeah, I should have mentioned that this continuous spectrum doesn't start from 0 energy. It's above a gap that's of order Q5. So at very low energies, you do have a discrete spectrum, but starting from some gap, you have this continuum, and you can compute this gap again from all three different perspectives, and you get exactly the same answer for this gap. So any further questions about this? Okay, so this description breaks down for Q5 equals 1, which is in some ways the most interesting case, because there, as we said, we have a dual field theory that's free. But a few years ago, Rajesh and his collaborators discovered that there is also another description of the string worldsheet using what's called the hybrid formalism. So originally that formalism was developed for describing Riemann backgrounds, but it can also be used for this NS background. And in this formalism, the CFT worldsheet turns out to be a sigma model on some superspace, so PSU 1 1, comma 2 at level Q5, again times a T4. And it turns out that this description is valid for all values of Q5, including Q5 equals 1. And what Rajesh and his collaborators showed is that for Q5 bigger or equal to 2, then in this description you can also see that you have this continuous spectrum. But for Q5 equals to 1, they showed that there's actually no continuous spectrum because of the properties of representations of this supergroup, PSU 112 at level 1. So in this case, there's no continuous spectrum. And that precisely, of course, in this case, we can't really trust supergravity. I mean, we have a highly curved space, so we can't trust the supergravity perspective, but it precisely agrees with what we thought from the CFT point of view, that in this case, we're supposed to just have this free orbifold, that it certainly doesn't have any small incident singularities. I mean, it could have had other singularities where these incident come together, but it turns out that those points are not really singular. So in this case, we'll really just have a smooth sigma model with no continuum, and that's consistent with this specific string theory at Q5 equals 1 being dual to that free orbifold. Okay, we'll discuss that in a bit more detail later on. So that was the quick review of what's known about the string worldsheet. So are there any questions about this part? Okay, so the final topic that I want to review is dualities. So, of course, we have a large group of U-dualities in type 2 on a torus. So, for instance, if we start with this type 2 string theory on T4, then that has an SO55Z group of U-dualities, which contains, of course, there's a T-duality group of the torus, which is SO44Z, and there's also just the usual SL2Z S-duality of type 2B string theory, but together they're enhanced when we have type 2 on T4 to this SO55Z group. So that's the full duality group when we started in type 2 on a torus. Now, we're looking at a specific background here where we also have these Q1D1 vanes and Q5D5 vanes. So, of course, generally this SO55 symmetry mixes their charges and turns them into other charges. So general SO55 transformations take us out of this specific choice of Q1 and Q5. But there's a subgroup gamma, which is some subgroup of SO45Z. So there's a subgroup that leaves Q1 and Q5 invariant, and that becomes then the U-duality group of this AdS3 background. So that's the duality group of AdS3 cross S3 cross T4 with some fixed values of the charges. And it includes, I mean, in the SNS description we have the SO44T duality, so that's a subgroup of that, but there's also some larger duality group that acts here. Now, let's discuss now what are all the moduli of this theory. So before we took the near horizon limit in type 2 to be on T4, we had 25 massless scalars or moduli, which lived in SO55R modded out by SO5 cross SO5 and by SO55Z. So that's the usual description of the moduli space of type 2 on a torus. So here we have 25 scalars, so 16 of them are just the usual moduli of the metric and B field of the torus. One of them is the dilaton, and 8 others are Ramon scalars, so various, just the usual Ramon zero form, and also the various integrals of the 2 form and 4 form on cycles of the torus. Altogether that gives 8 scalars. So those were the scalars before we took the near horizon limit. After we take the near horizon limit, it turns out that exactly 20 of them remain massless, and the other ones are fixed in the near horizon limit, as I already discussed. So the ones that remain massless are NSO54R, mod SO5 cross SO4, and modded out by this duality group gamma. And the ones that remain massless are these 16. If we look in the SNS description, then all 16 moduli of the torus remain massless, including the volume. The dilaton does not remain massless, it's fixed. I mean, at least the 6-dimensional coupling becomes fixed, as I described. And out of these 8 Ramon scalars, 4 of them remain massless, and the other 4 become massive, and they're also fixed. So all in all, in this background, we have 20 moduli, the 16 obvious moduli of the torus, and in addition, there are 4 Ramon scalars. They're also moduli, and those will be the moduli that allow us to go out of this singular regime and to blow up the singularities in the moduli space. So those are the massless scalars. In a specific AdS3 background with given fluxes, But I mean, the nice thing is that we still have this full duality group acting. So even though only the subgroup gamma acts on the specific AdS3 cross S3 with specific fluxes, if we look at other transformations that are not inside the subgroup, then they take this background to a different background that has different values of the fluxes. I mean, for instance, we can do an S-duality that will take the Rho1-1 fluxes to an SNS fluxes, but we also have S-duality transformations that take say, an SNS fluxes Q1 and Q5 to other values of the SNS fluxes, and it turns out that in fact different pairs of Q1 and Q5 are related to each other by U-duality transformations inside this SO55Z. And in fact, any pair Q1, Q5 where these two numbers are relatively prime so that they don't have any common factors, so they're all related by some U-duality transformation to the background where we just have, say, Q1, Q5, so the number of fundamental strings is Q1, Q5, and the number of fibranes is equal to 1. So all of these backgrounds are related by U-duality transformation, so even though previously it looked like these different backgrounds with different values of Q5 were completely different from each other, they are in fact related by U-duality transformations in this SO55Z group. Now you could ask how that's consistent because, as I said, naively these backgrounds look very different from each other. But the point is that previously when I discussed these backgrounds, I was focusing only on the subspace of their moduli space where I turn on only the metric and B field on the torus, but I was implicitly setting to 0 all the Rho1-1 scalars, and in particular, say the Rho1-1 scalar. And this duality transformation takes us from a vanishing value of this Rho1-1 scalar in one frame to a non-vanishing value in the other frame, and vice versa. So that's why the descriptions of the specific subspaces where the Rho1-1 scalar vanishes for different values of Q5 look very different from each other. But the full moduli space is really, well, it's the same moduli space. I mean, these are just dual descriptions of the same theory. So to illustrate how that works, let me say, describe all the theories from the point of view of the parameters of the theory with some flux n and Q5 equals to 1, and say so we have here some scalar, which we can take to be, say, the string coupling in the Rho1-1 description of this background, and we can then also ask what happens when we turn on the Rho1-1 scalar. So it's periodic, so its values go between -1/2 and 1/2. So previously I just discussed this subspace of the background. I mean, so this subspace is the one that's dual to this free orbifold. But the claim is that there are other subspaces of this background that are dual to these theories that have fluxes Q1 and Q5, again, at a vanishing value of the Rho1-1 scalars from the point of view of the other backgrounds. And the way that we avoid contradictions is that these subspaces live both at non-zero values of the Rho1-1 scalars and also at strong coupling from the point of view of this original Q1, Q5 theory. So for instance, if n is even, then there's some subspace here that corresponds to the n over 2 theory with chi equals 0 from the point of view of this other duality frame. And similarly, other backgrounds typically live here close to the real axis. I mean, so again, this background itself is parameterized based on string coupling, so it corresponds to a line in this frame, but that whole line lies at non-zero values of the Rho1-1 scalar and also at strong coupling, so that the full moduli space, it has, so again, here I'm just drawing a two-dimensional slice out of this 20-dimensional moduli space. But in the full moduli space, we have these subspaces. So we have 16-dimensional subspaces of the 20-dimensional moduli space, which correspond to these backgrounds that I described before, where we only have an SNS flux, for instance, with any specific value of Q1 and Q5. But all these subspaces are connected to each other within this full 20-dimensional moduli space. So we have to tune 4 of the parameters to go to this line, 4 of the parameters to go to this line or to that line. And a generic point somewhere in the middle, of course, would not have a good description in either of these formalisms, but again, they are all connected and they all live on the same moduli space. So that's the full picture.
So this duality, hello?
Yes.
So if we take a value of Q5 that was bigger than 1 at the pure NSNS point, so then
yes.
It has a continuous spectrum, and we map it to this Q1, Q5, comma 1.
Right, yeah, so that would sit on one of these arcs here.
Yeah, but that means that those spectra are also continuous, right? For a specific.
That's right. So from the point of view of the CFT, again, we have these 16-dimensional subspaces, and each of these subspaces, so that's a singular subspace where the spectrum is continuous. But at generic points, I mean, so the moment I turn on the Ramon-1 scalar a little bit, that already resolves the singularity. One can show in space-time, say that the spectrum of the long strings becomes discrete. I mean, there's a potential that pushes them towards the origin. So the moment we move away from these subspaces, the spectrum is discrete. So the spectrum is discrete everywhere except on these singular subspaces where it's continuous.
Sorry, just a follow-up question on that. Of course,
Yes.
the gap changes, right, when you do this? Because in the first case, the gap is at Q5, but now it's at either 1 or...
That's right. So each one of these continua has a different gap. I mean, so here you'd have a gap equal to 2, say here the gap could be 3 or 4, and so on. It depends on, right? So each of these string theories, so it's important to note that, I mean, of course, perturbative string theory is valid somewhere here in the original N1 frame, and then perturbative string theory in this frame would be valid somewhere here, or here would be valid somewhere here. So there's no overlap between the ranges of validity of perturbative string theory. I mean, so each perturbative string theory just captures some corner of this full moduli space, and it happens to capture here these corners where the spectrum is continuous with some gap, or here it captures this corner where it's not continuous. But that's only valid in some corner, and in the middle we have no description that's good. I mean, so there's no good perturbative description of general points in the middle. But again, this whole picture just follows from the usual U-duality symmetries of type 2 string theory, I mean, which are well understood for 25 years at least. So here I'm really not saying anything surprising for people who know U-duality. So any questions about this duality picture? So again, moving away from these singular manifolds, in space-time it corresponds to turning on these Ramon-1 scalars. On the worldsheet, we don't really know how to, I guess I already erased the worldsheet, but on the worldsheet we don't really know how to describe it well because we have to turn on Ramon-1 fluxes, and then the worldsheet is not really well understood when we go away from these slices. And in the space-time CFT, for Q5 bigger than 1, it corresponds to turning on these small incident singularities. Well, for Q5 equal to 1, it corresponds to turning on the blow-up modes at these orbifold singularities of this symmetric orbifold. So, I mean, it's important not to confuse, even though both of the singularities here look like orbifold singularities, in some sense they behave completely differently. I mean, for Q5 bigger than 1, we have these small incident singularities where the CFT is really singular, and here we have these free orbifold singularities. But both of them turn out that they're blown up when we turn on these Ramon-1 scalars, and those move us away from this orbifold point. So any questions about this?
Hello. I was wondering if you had any comments on the discrete part of the spectrum. The question I had specifically, actually, I have to say I don't know the update, is that you could, for instance, compute the index on the symmetric product orbifold, and you find that could be completely reproduced just by computing the index on just.
Sorry, I can't hear you very well. Maybe you can talk closer to the microphone.
I was asking if you had any comments on the discrete part of the string spectrum, not the continuous part, and just to motivate that question, can you hear me? Yeah. Can you hear me?
Well, so of course, in any regime where perturbative string theory is valid, we can compute the full spectrum in perturbative string theory, and of course there are BPS states that are the same anywhere in this model A space, and we can follow them and see that they're the same in all the different corners. But yeah, general states that are not BPS, of course, their dimensions would change when I move around here. I mean, and in particular, the states that are continuous here, I mean, become discrete and move around.
The specific question I had is that one could compute the index in the symmetric product orbifold CFT.
Yeah. So the index, of course, is fixed. I mean, the index only counts BPS states, and those are exactly the same. So it's the same in the symmetric product as if I compute it in gravity. I mean, assuming that I use only states right to gravity approximation, and it's the same in all these different string theories.
Yeah, but the question I had is, in fact, it's not so clear to me that the index is the same in the string theory. In gravity, of course, if you take gravitons and you do a particle them like Jan de Boer did many years ago, and you find an index that matches the symmetric product orbifold. But some of these discrete states in the string theory, I thought they can contribute to the index, and at least it's not clear how that contribution gets cancelled. I mean, presumably it does get cancelled.
So which states are you asking about? Sorry.
States in the discrete part of the SL2R Westermino-Witten model. So
okay, that's a good question. Yeah, I don't think that they give rise to any BPS states, but I'm not completely sure. But yeah, anyway, I mean, of course, again, it is the same CFT, so any states that we can control necessarily have to fit in correctly. And yeah, as far as I know, it does match. I mean, there was this recent paper in particular of Murthy and Rangamanian and collaborators where they checked it, I think. I mean, and as far as I know, the index does match between all these different descriptions.
Yeah, Ofer, I think, of course, on the T4, there's something very trivial that happens, which is that the usual index vanishes for all perturbative states.
Yes.
No, even that supersymmetric index, there's a new, whatever, there is a special.
Yeah, that's right. It has to take a more elaborate index. Yeah, that's right.
No perturbative states contribute to it. Only the non-perturbative states contribute to it. This is this Maldacena-Moore-Strominger index.
Yes.
T4.
Right.
So I think in that sense, there's a trivially, it's okay. K3, I'm less sure. I don't know the situation with K3. But
Yeah.
for the T4 case,
Okay.
at least I think it's in a sense.
Yeah. Yeah, okay, thanks. Yeah, so, right. But in any case, all the VPS states that one can compute reliably match, and yeah, non-VPS states in general, of course, do not match between these different descriptions. Let me just finish this review by one thing that may be confusing at this point. I mean,
that you drew about the figure G6 and chi.
yes.
So all these loci that you drew have discrete spectrum, right? Because it's n comma 1.
That's right. Well, this line has a discrete spectrum, and everywhere else except for these arcs, only on these arcs the spectrum is continuous.
On the arcs, the spectrum is could you say?
So again, how many arcs we have depends on how many decompositions of n you have into relatively prime integers. But for every decomposition of n into two relatively prime integer, you have one of these arcs, which maps to the Q1, Q5 background with chi equals 0, and then that background has a continuous spectrum. So for every decomposition of n into two relatively prime integers, you have a singular subspace of the moduli space.
But the chi is non-zero on those semicircles, right? Because
Right, yeah, there's no intersection between these different arcs, of course. Yeah, each one of them is completely separated from the others. So these orange lines here, which I hope are visible, are the subspaces where we have chi equals 0 in some description, either in Q5 equals 1 or in Q5 not equal to 1, and these subspaces do not intersect in any way. Okay, so one final confusing issue is that, as I said, these different CFTs with different values of Q1 and Q5 are all continuously connected to each other by exactly marginal deformations if Q1 times Q5 is equal. But previously I said that they have different symmetries because I said that these theories have U1 to the 4th level Q1 and U1 to the 4th level Q5, and of course that's not the same as theories with different values of Q1 and Q5. So how is that possible? So it's actually, well, so the story is that actually these CFTs don't just have 20 moduli, so they have the 20 moduli that I described before, but they also have 64 additional exactly marginal deformations that look like JJ bar deformations. So whenever we have a U1 left moving current and a U1 right moving current, then their product is an exactly marginal deformation. And in this case, we have 8 left moving and 8 right moving currents, so that we have 64 additional exactly marginal deformations of the form JJ bar, which just act on these U1 sectors. I mean, so here they, in some sense, just act on these periodic scalars that I described before. And the way that it's consistent that the levels of these U1s change is you can show that when I change the moduli, when I change the usual 20 moduli to go from one of these subspaces to the other subspace, it turns out that I'm also at the same time turning on very specific JJ bar deformations that one can compute. And those deformations mix these different U1s in such a way that when I get to some new point in the moduli space, then and I diagonalize the basis of U1s at that point, then they have exactly these different levels. So one can show that by appropriate JJ bar deformations, one can interpolate. So this allows to interpolate between, say, U1 level 1 plus U1 level n to some, so we can continuously interpolate the U1 level Q1 plus U1 level Q5 by JJ bar deformations. And that's what's going on there. So that's how it's consistent with the symmetries that I described. So that's basically the end of the review part of the talk. So yeah, let's see, can I have maybe 15 more minutes for the rest of it.
Maybe 30 more minutes, or yeah.
Oh. Okay, we'll see
Yeah,
how long
yeah.
it'll take. But anyway, I hope we can continue for at least 15 more minutes or something.
Yeah, sure.
Okay, sure. So that ends the basic review part. So I hope I described all the basic properties of these backgrounds. So are there any questions about this before I go into the specific questions that I wrote down in the beginning?
Yeah, I think you can go on.
Okay. So now we'd like to discuss three confusions that we had when we were considering this picture. So the first confusion involves this mapping between an SNS background with Q5 equals 1. So we said that that's dual to this symmetric orbifold of T4 to the power Q1 with SQ1 plus this extra T4. So this is this very nice picture that Rajesh and his collaborators discussed for how to reproduce the 1/n expansion of the symmetric orbifold and how to match it to the perturbation theory in this SNS background. So the way that it works is that in this symmetric orbifold, you can discuss correlation functions of various twist operators. And then there's a general story that's valid for any symmetric orbifold, and I guess was first discussed by Lunin and Mathur 25 years ago, that for any symmetric orbifold, if you have correlation functions of twist operators, then you can go, then each of these twist operators corresponds to some permutation between the different Q1, so you can think of it as having Q1 sheets living on the manifold that the CFT lives on, and then around each of these twist points you have some permutation of these sheets, so you have some permutations here, and then you have to join together the permutations in such a way that, of course, they're consistent with the global structure of this manifold. And again, it's a general property of symmetric orbifolds that when you do that, then you can translate these correlation functions with these twists into correlation functions of the original just T4 CFT, but living on some more complicated covering space that you get by just sort of going to the covering space of all these with all these permutations and just mapping it to some non-singular manifold. So again, that's a long story that I hope most of you heard about in other contexts. But anyway, the bottom line of that is that in any symmetric orbifold, we have this 1/n expansion coming from looking at the different, well, we would get in general manifolds of different genus by joining together these permutations at the twist operators in different ways. So that gives rise to a 1/n expansion. And what Rajesh and his collaborators show is that 1/n expansion maps exactly to the perturbation theory in G string in this SNS background. In particular, in this case, I remind you that in general, in the SNS frame, we had the G6 frame. G6 squared was Q5 over Q1, and in this case, this is just a 1/n, so that indeed we expect this 1/n expansion of the symmetric orbifold to precisely match to the perturbation theory of this SNS background, and indeed they showed that they do match up to some caveats, which I'll discuss in a moment. But the first confusion about this that I want to discuss is that in this SNS background, as we said, we have this G6 squared parameter, which is fixed to be 1/n, but we also have the 10-dimensional string coupling, which in this case is given by the volume of the T4 in string units divided by n. Now, in general, this duality is valid for any volume of the T4, and in fact, one can show that the volume of the T4 here in this SNS frame is exactly the same as the volume of this T4 here, which appears in the symmetric product, so we can just take that to be anything we want, and we have a mapping between the two sides for any value of that volume. But we see, and in particular, that volume doesn't have to be smaller than n. I mean, it can be anything that we want. And in particular, we can discuss what happens if the volume of the T4 is not much smaller than n, and in particular, it might even be bigger than n. And we see that in that case, the string perturbation theory here breaks down. So even though the 6-dimensional string coupling is small, when the volume of the T4 is very large, then, I mean, the 10-dimensional string coupling is more relevant for analyzing what's going on. And we see that in this regime, the 10-dimensional string coupling becomes large, so that this theory is actually not weakly coupled in this regime. But on the free orbifold side, we do still have a free orbifold in this case. So one question is just how is that consistent with the mapping between these two sides? And so that was the first thing that we were confused about. Now that turns out to have a simple resolution. I mean, so as I mentioned, this 1 over n expansion maps here to looking at correlation functions. So the leading order would correspond to lifting this to a covering space, which is a sphere. So we would map the correlation function to some correlation function and the T4 CFT on S2. And then there's 1 over n times a correlation function of this T4 CFT on a torus, and so on for all the correlation functions here, left by going to the covering space to some correlation function with just a T4 CFT, but on, in general, higher genus manifolds, where this 1 over n corresponds to the genus, I mean, so that we can identify who the string rule sheet and this NSNS approach. So that's true for any value of the volume of this T4. But the point is that when we have a sigma model on a T4 and that T4 becomes very large, then already the partition function of a T4 CFT on a torus scales like the volume of the T4. I mean, so that's probably familiar if you just look at the partition function of just a compact scalar on a torus, then that scales like the radius of the circle for a large radius. So just the partition function here would already have an extra factor of VT4, and the correlation functions, since we're not normalizing them here by the partition function, they would also have this extra factor of VT4. And similarly, at the next order in 1 over n, where we'd have the correlation function on a genus 2 manifold, then that it turns out that again we have 0 modes of the scalars of the T4 that can have any momentum around the cycles of this manifold, and that gives rise to an extra enhancement, in this case by VT4 squared, and so on. So that it turns out that in the large volume limit, even though we still have a 1 over n expansion of this free orbifold, then that expansion is really also on this side an expansion in VT4 over n, exactly consistent with what we find also on the string theory side. So on both sides, we see that even though formally we have a 1 over n expansion, the expansion in practice for very large volumes turns out to be an expansion in the volume over n, and therefore it breaks down on both sides. So that resolves this apparent mismatch between the two sides. Now there's another aspect of this mismatch that on the string theory side, if we take VT4 now to be much bigger than n, then the 10-dimensional string coupling in this NSNS frame becomes much larger than 1, and then it's very tempting to do an S-duality transformation to the S-dual frame. So in the S-dual frame, we would now have a coupling that goes like n over v, and which would be much smaller than 1. So it looks like in this regime, we would have a weakly coupled description in the Ramon-Ron frame. So naively, from this point of view, it looks like this free orbifold correlation function should rearrange themselves in a different way so that they would have an expansion in n over v. But if we actually compute them, I mean, yeah, it's a free theory, we can compute anything we want, and we see that they don't actually have an expansion of this type. So even though higher genera dominate, I mean, this expansion in the genera is always truncated at some finite genus, and there's no actual expansion in n over v of the correlation functions. So how is that consistent with the string theory side, where naively we can take the Ramon-Ramon coupling to be as small as we want? So the issue is that if we really look in more detail at what happens to the Ramon-Ramon frame in this limit of very strong coupling, we see that it actually becomes singular. So I guess I still have here these formulas. I mean, so naively, if we try to take G tilde 10 to be very small in the Ramon-Ramon frame, then the radius of AdS space of the S3 becomes very small. I mean, so obviously we cannot really trust these formulas anymore. And I mean, if we would try to trust these formulas, then we would find that the 10-dimensional G Newton in units of the AdS radius is not small, but it's actually very large in this limit. I mean, this goes like V over n. So even though naively the string coupling here becomes small, then in fact the formulas that we use to analyze that background are not valid anymore, and this background is not really weakly coupled, even though the string coupling becomes very small. Now, to those of you who are familiar with the duality between n equals 4 supreme modes and AdS5 crosses 5, also there's a similar phenomenon. So if we discuss the case of AdS5 crosses 5, so also in AdS5 crosses 5 in 2 string theory, we can take the limit where the string coupling goes to 0, and then in the dual CFT that's the same as taking the n1's coupling to 0, so that we just get a free field theory. So naively, we may think that in this limit we always just get a free string theory, but in fact that's not true, because we know in the free n-Mills theory, we know that if we look at the expansion of gauge invariant correlation functions, they do have a non-trivial expansion in powers of 1 over n, even in the limit of a free theory where the Mills coupling goes to 0. And so similarly, on the AdS side, also even when the string goes to 0, we're still left with a non-trivial expansion in 1 over n. And if n is not large, then the theory is not really weakly coupled, even though formally the string coupling goes to 0. So what we claim is that the same thing happens here, so that when Q5 is equal to 1 in particular, or in general for small values of Q5, even though we try to take the limit where the one-to-one string becomes weakly coupled, it is not actually weakly coupled, and therefore we do not have a contradiction with this orbifold picture. So that was just a confusion that we had that again is resolved by the fact that the perturbation expansion here is in V over n, and the one-to-one description for small Q5 is not really weakly coupled, so we cannot use it to get a contradiction. So are there any questions about this first issue? Okay. So if not, let me go on to the second confusing issue.
Okay, sorry.
Sorry, question?
So if you take Q5 to be 1, and then like, can you do something, I don't know, if can you comment, for example, in the plane wave limit, and then just add like some Ramon, and then like, do you get, I don't know, similar picture? Like, is it?
Yeah, and I don't. Of course, you can try to analyze this directly in the one-to-one string theory. I mean, but there I don't understand the world sheet of the string well enough to really see if it that it breaks down. I mean, so also in AdS 5 versus 5, I don't know how to see directly from the world sheet that in this limit of the string goes to 0, we don't really have a perturbation theory in the string, but it actually becomes a perturbation theory in some other parameter. But the claim is that we know from the field theory side that that's what has to happen, and we just don't control the world sheet well enough to see it directly in the string theory.
Mm-hmm. But I thought like in the plane wave limit, somehow you can actually do like exact calculations, right? Even for like, even like when you have like Ramon fields and all this.
Sorry, can you repeat the question?
Like, if you work like, if you take the plane wave limit, even if you have Ramon fields, you can actually do some exact calculation, right? Like, so I don't know if there is any work, but I'm just asking, like.
Yes, so that's true, but I think that in the plane wave limit always involves taking n to infinity. I think, and also here it would involve taking Q5 to infinity. So I don't think you can be in the plane wave limit and also take Q5 equals to 1. So then that's how you avoid getting contradictions.
I see. Thanks.
And the plane wave limit also always has to rescale also the curvatures to become small. Any other questions about this? Okay, so the second issue I want to discuss is what actually does the string perturbation theory compute in this NS background. So we said that maybe it matches to the 1 over n expansion of this free orbifold, but in fact the situation is more subtle. So on the CFT side, we saw that our CFT had two discrete parameters, Q1 and Q5. But when we looked at the string world sheet in the NS background, then the string world sheet only had one discrete parameter, which was Q5, and Q1 did not appear at all as a parameter of the string world sheet. And on the other hand, if we do look at the world sheet, then it looks like we just have a continuous parameter, which would be the string coupling, because on the world sheet, as usual, we can just add an arbitrary coefficient in front of the Euler characteristic on the world sheet. I mean, nobody tells us what's the value of this, even though in spacetime we saw that the delta was fixed. On the world sheet, we can still choose any continuous value for this parameter, and it looks like we can vary the string coupling as we wish. So it looks like we have a mismatch between the parameters of the CFT side and the parameters of the string theory side. And that can be made more precise by trying to compute on the CFT side what is the central charge of the spacetime CFT, say by looking at the two-point function of energy momentum tensors. And one finds that the central charge, even though on the CFT side we saw that the central charge was a 6Q1, Q5 plus this high order correction, here we find that it's given by 6Q5 times the expectation value of some operator, but that expectation value is not just a fixed number. I mean, it has fluctuations, or it has higher moments, and so on. So it's not given by any fixed number. So that was a confusion that dates back already to the early days of AdS CFT, of precisely how does this world sheet theory with its continuous parameter and unfixed value of the central charge map to the CFT, which just has a discrete parameter and a fixed value of the central charge. So that's one aspect of this confusion. The second aspect of the confusion is that, as I said, the perturbation theory in the SNS background naively maps to the 1 over n expansion of this symmetric orbifold. But it turns out that this 1 over n expansion does not exactly match with string perturbation theory. For instance, so I didn't go into any details of precisely how this matching works, but the way that it works is that single string states map in the symmetric orbifold side to operators in a twisted sector or twist by a single cyclic permutation, say of length W, and then all the other elements map to themselves. Yeah, sorry, question?
Hi, Ofer. Sorry, a naive question about point 1.
Yes.
Sorry, what is the confusion? This is the world sheet central charge. So why should it match with the space-time central charge? So I mean, why is it a confusion exactly? I mean, there's some
well, it's a confusion because here it looks like we should have an exact mapping between the two sides. I mean, so the two sides should have the same parameters. I mean, obviously, if we want to say that we have an exact matching, then everything that we compute should match, and in particular, say the value of the central charge should exactly match, and the parameters should match. So you could say that maybe there's some non-perturbative effect that somehow discretizes this G string, so that maybe we don't see it, but somehow non-perturbatively maybe it gets fixed. But even if that was the case, then you can see that that's still not enough because the value of the central charge is still a fluctuating operator here. For instance, the expectation value of the world sheet of the central charge squared is not just c squared. I mean, so even if you assume that non-perturbatively this parameter is somehow fixed, then the two sides still don't match. So this is really a mismatch between the parameters of the two sides, which
of the space-time
should be the first thing that we check in AdS CFT.
So this is the central charge of the space-time theory as computed from the world sheet. This number 6q5 times expectation of I.
Sorry, can you repeat the question?
Sorry, this number that you wrote below, 6 times q5 times expectation of I. Like this is the central charge of the space-time theory as computed using the world sheet.
Yes, exactly.
I see.
And we see that it doesn't match with a space-time CFT because even though maybe on average it would match if you fix G string to a specific value, then it would still fluctuate. I mean, so it would get higher order corrections. So that's one mismatch that we see. And the other mismatch is that if we go into more details, which again I won't have time to discuss here in detail, but single string states map in this mapping to the symmetric orbifold to twist operators by single permutations inside this SN group that we're dividing by. And for instance, if we have a state with two strings here, then that would map to a twist operator by two permutations, say 1 up to W1 are permuted, and then W1 plus 1 up to W1 plus W2 are permuted, and the other
couldn't the central charge have to do with non-perturbative effects? I mean, that you might not be able to capture in the world sheet?
Yeah, I mean, in principle, it's possible, but I mean, but I think we can. I think I think the non-perturbative corrections would have to be very strange to be able to fix all the correlation functions to agree, and in any case, I mean,
one place a concrete mismatch, if you could do it, would be by computing the growth at high energies, right? And the central charge controls that growth, and if you could find a mismatch, you would really be in trouble.
Right, but those of course we don't know. Those of course are non-perturbative. So yeah, that I don't know how to match. That's right. But anyway, I mean, I'll describe a resolution. I mean, so I think for many years people believe that maybe indeed non-perturbative effects resolve this, but it's been understood for the last 10 years that I mean they can be seen. The resolution can be seen already in perturbation theory. So that's what I'll describe.
Okay.
I mean,
Thank
so
you.
Even though it could have been resolved by non-perturbative effects, in fact, one can see the resolution already perturbatively. So again, one mismatch is just in the number of parameters, and the other mismatch is that the single string states match. So this one is for any value of Q5. This other mismatch is special for Q5 equals 1, so that one was only realized in the last few years after the Q5 equals 1 case was well understood. So in this specific mapping, single string states map to single cycle permutations, while two string states map to two cycle permutations. And then, for instance, you could ask what would be, say, the two-point function of a two-string state. So suppose we look at just a two-point function of a two-string state with itself, with the same two strings on both sides. So that starts from some disconnected piece, which would be the product of two correlated functions of one string, and then there are corrections from connected diagrams. So that's obviously true on the string theory side, that we would first have a disconnected contribution that would be the product of two spheres, and that would scale like 1 over g string to the fourth, and then we'd have this connected contribution correcting it. Now the same is true also in this orbifold. I mean, so here we have a correlation function of two operators where we have this twist by these two permutations. And one way to connect the world sheets is just that we connect this permutation to the other one on the other side, and similarly for these other sheets, so that we get a disconnected diagram. But it turns out that the precise coefficient of that disconnected diagram, so in string theory, the ratio between the connected diagram and the disconnected diagram, in string theory, the disconnected diagram is precisely this product of two single string states. But if we compute it in the symmetric orbifold, we find that the disconnected contribution to this correlation function is not exactly the same as the product of two-point functions of single string states, essentially because of various combinatorial factors that here we have to choose which W sheets out of n participate in this cycle. But for the two-string states, we have to choose both these W1 sheets and these W2 sheets to come from the same n copies of the CFT. So we can show that the coefficient of this in the orbifold side, the coefficient of the disconnected contribution is not 1, but it's 1 plus something over to 1 over n, and then it has also higher order corrections. So if we try to extend this matching between the 1 over n expansion of the free orbifold and the expansion of the string perturbation theory to higher orders in 1 over n, we see that it actually fails. So what's the resolution of these two confusions? So it turns out that the two confusions are actually resolved by the same thing, and the claim is that string perturbation theory is actually not dual to the theory with a specific value of Q1, but rather it's dual to a grand-canonical ensemble of these CFTs with different values of Q1. So if we denote by, say, Z and J, the partition function of the CFT with n units of, say, let's start from Q5 equals 1. So for Q5 equals 1, if we denote by Z and J the generating function of correlation functions and the CFT with Q1 equals to n and 1 5 brane, then we can define a grand-canonical ensemble by considering the sum of p to the n for some parameter p of these partition functions. So this is, if you want, just some Legendre transformation with respect to this parameter n, from 0 to infinity. So, of course, in principle, that is just a repackaging of the same information, but in this repackaging, instead of having this discrete parameter n, we now have this continuous parameter p. And it turns out that what string perturbation theory actually computes is the correlation functions coming from this generating function in the grand-canonical ensemble, where p is related to 1 over g string squared, rather than the correlation functions with a specific value of n. So that explains both why in string theory we have a continuous parameter instead of a discrete parameter, so that exactly corresponds to what we have in this grand-canonical ensemble. And one can show that when one looks at these correlation functions and does their transform to the grand-canonical ensemble, then in that ensemble, it turns out that these two string states do exactly factorize with a coefficient which is exactly 1, such that we do indeed have a precise match of all the correlation functions to all the orders in perturbative expansion in P between the free orbifold side and string perturbation theory. So that's the claim is that this resolves those confusions, and it can be shown explicitly for many different correlation functions. So any questions about this?
Yeah. So in the board above, is the confusion that the connected part is supposed to be 1 over n squared, whereas the orbifold gives the 1 over n?
No, the connected part is always 1 over n squared on both sides. The confusion is about the disconnected part. I mean, so the disconnected part, its coefficient naively should be exactly 1 without any extra 1 over n corrections, but it turns out that it's not exactly 1, but the disconnected part also gets 1 over n corrections, even though it's not supposed to. So that was the confusion, and it turns out that doing this transform to the grand-canonical ensemble exactly gets rid of those things on the nose and gives a coefficient which is 1, as one would expect from string perturbation theory.
But shouldn't the disconnected part get a correction from, let's say, the torus 2-point function?
Well, in general it could, but they have a different form. I mean, so the connected, I mean, in this mapping of the free orbifold to world sheets, I mean, we do understand how to map different diagrams to different topologies. I mean, and there is really a distinct contribution here coming from a disconnected topology as opposed to the connected topologies. I mean, the connected topologies do just map to the connected topologies there. I mean, so you could try to say that there's some mixing which resolves it, but we tried that and it didn't work. And it turns out that the only thing that does work is going to this grand-canonical ensemble, which again has also other motivations. And once we go to this grand-canonical ensemble, we do get a precise match between the two sides, both in terms of the parameters and in terms of the correlation functions.
Asking about your statement that the disconnected part is supposed to be exactly 1.
Yes.
So the
part is of course it depends on being able to exactly identify what you mean by the disconnected part. I mean, and of course, in principle, the two-point function itself could have one-to-one corrections and so on, and so one has to be careful about exactly how one defines it, but the statement is that it is a well-defined statement both on the free orbifold side, whether you get a contribution from a covering space which is disconnected or connected, and of course in string theory it's a well-defined question, do you get disconnected or connected contributions? And one can show that there cannot be any mixing between the two, and that if you try to compute in the naive ensemble, then the results don't match, but in this grand-canonical ensemble, they do precisely match.
And I also had one question. So in low enough dimensions, the decaying part and the growing part of fields can interchange. Like for a gauge field in AdS2, the part that is proportional to the charge is leading compared to the chemical potential. So for the B field in 3 dimensions, it should be similar.
Yeah, that's right. So that's exactly the next thing that I was going to say. So one can ask, how is this realized from the gravity point of view? I mean, so from the gravity point of view, naively we just had this fixed flux. So we said that this flux of star F3 on S3 cross T4 was exactly equal to Q1. And it turns out that on the gravity side, in this case, you can impose one of 2 different boundary conditions for this flux. So one boundary condition is the fixed flux boundary condition. That's what we get from the near horizon limit, and that's also what we would get, say, if we do perturbation theory in the Ramon-Aron background. I mean, so the perturbative Ramon-Aron background string, that does have a fixed value of this Q1. I mean, so there is a fine theory that just has a fixed value of Q1. But it so happens that that's not what the S string perturbation theory computes. And there's just another way to, instead of fixing the total flux, you can fix the potential of this field at the boundary. So in this case, both choices are legitimate. I mean, again, they're just related by this Legendre transform, essentially. And another choice is just to fix this potential for this free form instead of fixing its flux. And it turns out that fixing the potential is what corresponds to the string perturbation expansion, while fixing the flux is what we would naively get from the near horizon limit, and that's also what corresponds to string perturbation theory in the Ramon-Aron frame. I mean, so I don't know from first principles how to see that the NS string perturbation theory corresponds to these different boundary conditions, but we can see from answer analysis that that has to be the case.
But both of these modes are normalizable?
Well, I think it's a bit, well, both of them in some sense are maybe non-normalizable. I mean, both of them are not fluctuating. I mean, so both of them are just fixed. But you can sort of fix, well, okay, I mean, yeah, I guess in some sense both of them are normalizable in the sense that you can either fix this or fix that, and then the other one would fluctuate. So yes, so in that sense, both of them are normalizable. And again, they're just related by this very simple mapping. So that's the claim. Again, on the CFT side, of course, I mean, there's certainly nothing wrong with a CFT for a fixed value of n. It just so happens that that's not what string perturbation theory in this NS background computes. So any further questions about this issue of the grand-canonical ensemble? Okay, so since it's running late, maybe let me be very brief on the third issue. I mean, so the third issue that confused us is how is it possible for the CFT to have this extra decoupled sector? I mean, so here in this case, the CFT is really a decoupled product of the symmetric orbifold times this extra T4, and they don't really talk to each other. When we go to the alibis of Q5, then it's not a completely direct product, but it's still true that, I mean, it's a semi-direct product. I mean, so it's still true that we have correlation functions of this part that don't talk to the rest of the part. So how is that possible? Of course, we're always taught that in string theory we cannot have any decoupled sectors because everything couples to gravity. So the resolution of this issue is that, as I already mentioned, this T4 and the other U1s map in space-time to U1 Chern-Sandwich theories that live on AdS3, at least with low energies. And of course, the special property of Chern-Sandwich fields is that they don't couple to gravity. I mean, they really give us a topological theory that is not even coupled to gravity. So in this case, we can see also on the gravity side that we have these Chern-Sandwich fields that are really completely decoupled from gravity. And in this case, for Q5 equals to 1, the specific U1 fields at level 1 are even completely decoupled from everything. And so the claim is that in this case, unlike the standard law, we do really have in these string theories completely decoupled sectors that are just described by U1 Chern-Sandwich theories on AdS3, and that don't talk to the rest of string theory. And so I mean, I could give a bit more details of that, but I mean, essentially that's the bottom line is that in this case, this standard law that we can't have decoupled sectors breaks down, and the special properties of U1 Chern-Sandwich theories on AdS3 precisely match with the properties of these decoupled sectors on the CFT. But since it's late, let me not go into details of that, so let me just summarize. So I tried to review here various different aspects of this type 2 string theory on AdS3 cross S3 cross T4 and its dual CFT. And we saw that even though many issues are well understood, then there are also some confusions, but at the end of the day, also these confusions can be understood, and I think there is a completely detailed understanding of precisely how the two sides map to each other. Now there are still a few issues that are not clear. I mean, so one issue that's not completely clear is what is the precise grand-canonical ensemble, which is dual to string theory in the case that Q5 is bigger than 1. So for Q5 equals to 1, we just sum over all values of Q1, but for Q5 bigger than 1, it's not clear yet exactly which grand-canonical ensemble we have in an SNS perturbation theory, whether we sum over all values of Q1 or just over values that are relatively prime to Q5. So it's not clear what's the answer to that. And in principle, if we were do sophisticated enough computations of the string theory, we should be able to map them and see exactly what they map to. But of course, again, for Q5 equals to 1, it's not a free theory anymore, so it's much more difficult to compare the two sides, but there should be some well-defined answer to this question. Of course, a more challenging question would be to understand what happens to these theories when we go away to these, when we go away from these regimes where we have string perturbation theory. So string perturbation theory is only valid on these small subspaces where we have vanishing Riemann-Roland fields, and probably the best method to try to do that is by using integrability. I mean, as Rajesh and Matthias Gabriel tried to do, or there are various other suggestions for integrability in these theories. So hopefully, eventually, integrability will enable us to extend our understanding from these small corners of the moduli space to maybe be able to control at least some things in the full moduli space of these theories. And finally, there are various generalizations of these theories. So one generalization, which is relatively straightforward, is to take to be on AdS3 cross S3 cross K4, sorry, cross K3, which is already mentioned by Rajesh. And so that example is very similar to this one. Also there, we have for Q5 equals to 1, again, it's a free orbifold. And again, we have dualities that relate to different values of Q5. So that example is very similar to the one I discussed. The only main difference is that we don't have this extra decoupled sector in this example, but otherwise they're very similar to each other. Then we can go to more complicated examples. We can discuss type 2B on AdS3 cross S3 cross S3 cross S1, which has some large n equals 4 algebra. So in this case, it's still true that the Q5 equals 1 theory is a free orbifold, so that theory is well understood when one of the fluxes on S3s is equal to 1. But in this case, we don't have dualities that relate that to the other values of the flux. So in that case, we still don't understand what's the proper description of the CFT for generic values of the fluxes, because we don't have this relation between them. Now, if you look at other backgrounds like type 2A on AdS3 cross S3 cross T4, cross K3, or say related to the heterotic string on AdS3 cross S3 cross T4. So those cases we can also analyze from the worldsheet point of view, but in this case on the CFT side, it's not, there's no free CFT at any point in the parameter space of these theories, not even for the analog of Q5 equals to 1. So in that case, much less is understood from the CFT side about these theories, and of course it would be nice to understand them better. So that's all for now, so thank you, and sorry for going way over time.
Yeah, let's thank him for the nice talk. Are there any final questions?
So, Ofer, do you remember what the large distance so if I solve for the the B field in AdS3 and we look at the classical solutions in the asymptotic limit of AdS3, what do they behave like? Like as power of R? This is
well, I don't remember offhand, but I mean it can easily be worked out. I mean, so it's
okay.
I mean it's similar to an electric field on AdS2, I think. I mean, so it's probably behaves the same way, but yeah, I don't remember the precise powers.
And one which is linear, probably. But somehow I would have thought that then you're forced to sort of fix the linearly growing piece. Because
yeah, I mean that's also what I thought, but yeah, but it turns out that it's not true. I mean, again, at least on the string theory side, we see that we definitely we're not forced to that. I mean, and also, I mean, the CFT is certainly well defined without it. I mean, so, I mean, okay, maybe of course there is a subtle point here that, I mean, I defined here this grand-canonical ensemble, but this is really only well defined perturbatively in P. I mean, of course, this perturbation expansion doesn't really converge like any perturbative expansion. I mean, so one could say that this ensemble is not really well defined non-perturbatively, and I think that's true. But at least perturbatively, I mean, there's no problem. I think there's no problem with just constructing the sum, and I think that also on the gravity side, if you just formally choose to fix the potential, then you would formally get exactly this sum. So, I mean, again, it may look like a sum over completely separate theories, which we don't usually do, but here, somehow string perturbation theory magically does that, and so it does seem to be consistent, even though it's not something that we would naturally tend to do from the gravity point of view. So yeah, sorry if that's not completely satisfactory, but that's the best I can say.
If there are no further questions, let's thank him again.
Okay, so thank you very much, and I hope to come in person sometime for a real seminar.
Thanks for the boat talk.
Okay, so bye.